Hello everybody, and welcome back to another geometry lesson. Today we are taking a look at section 10.6, segment relationships in circles. So, much like the previous few sections, we're going to start by talking about a couple of definitions to help us understand what's really going on inside of these circles. And the sort of big player of today is going to be the chord. As you'll recall, a chord of a circle is any line segment that cuts through from one side of a circle to another side of a circle. But what happens when you have multiple chords cutting through? Well, you get some very interesting relationships, as we've already sort of seen with a couple of the previous lessons. Let's say I have a chord here. I'm going to name A, B, and I have another chord that I'm going to name C, D. I want to call their intersection point E. Well, what you really have, even though you only have two chords, is four different chord segments. A piece of a chord that intersects at some part, or some point. The segments of a chord theorem says the following, and this is a very interesting dynamic. If you compare the two segments of one chord and multiply them together, they're going to equal the product of the two segments of the other chord. Meaning, chord EA times chord EB, so I'll write it as EA times EB, is going to actually be equal to EC times ED. Basically multiply the pieces of a chord together, and it'll equal the product of the pieces of another chord. The actual definition is as follows. If two chords intersect inside a circle, then the products, meaning multiply, of the segments of each chord are equal. Multiply those pieces of a chord together, and you've got a recipe for solving. Now, some of these problems will be a little bit easier than others. For instance, if I just threw together a problem that looks like this, let's say I had a circle here, or what should be a circle, looks awful to be honest with you. I threw together some segments, and I said this segment is 3, this segment is 6, this segment is 18, solve for x. This would be a very easy problem to do. Multiply the segments of one chord, so 3 times 6, times equaling the segments of the other chord, 18 times x. We could solve this for x very quickly. 18 equals 18x, divide by 18, and we would get x equals 1. Nothing too crazy. Something that is a little bit crazier is what happens at the bottom of this page of our notes. So if we take a look here, all of a sudden, we've got something a little different, a whole different beast. Exercise 1 asks us to solve for x and then find the length of each chord. We know that the segments of each chord can be multiplied together and set equal to each other. So we can say x plus 2 times x plus 1 equals x times x plus 4. As we go through this problem, some things will have to happen. X plus 2 times x plus 1 will have to actually double distribute. We'll end up getting x times x is x squared, x times 1 is 1x, 2 times x is 2x, so if I have 1x and 2x, I'll have 3x in total, and 2 times 1 is 2. On the other side, x times x is x squared, x times 4 is 4x, you may end up with a quadratic expression. We get lucky in this problem, though, because in order to solve a quadratic, we have to move all the x's to one side, and in many cases, move all the numbers to one side. I'm going to subtract x squared and 4x from both sides, and we'll see that this problem actually works out very nicely for us. Subtract x squared, and they cancel on both sides. Subtract 4x, and you end up with negative x plus 2 equals 0. And that could just be simplified to negative x equals negative 2, or x equals 2. To solve for the length of each chord, you just have to plug in 2. So, for segment MN, x plus 2 will give us a total of 4. For segment x plus 1, 2 plus 1 gives us 3. So we know that that chord is 7 units long. And similarly with KJ, NJ goes x plus 4, which we know is 2 plus 4, or 6, plus, well, x is just 2. And what's 6 plus 2? Well, that gives us 8. I want you to pause the video and give B a shot. I'll leave this up here on the screen for you. Pause the video, see what you can do. How'd you do? When we solved, we should have gotten 4 for x, we should have gotten 14 for the length of AB, and we should have gotten 13 for the length of QP. That's it. Now, there might be problems that show up in your homework where you will have to factor or complete the square or solve it algebraically or even use the quadratic formula. But we're not going to talk about those right now. Instead, I want us to shift gears somewhat and talk about the other types of segments you can have. So just like how we have chord segments, we can also have the segments of a tangent or of a secant. There's all kinds of segments that we can have. So let me show you the 3 types that we're going to be talking about right now. Let's say that on this circle, I draw a tangent that goes this way, and it goes off forever. Let's also say that I have a secant that cuts through this, like so. A tangent segment is going to be the part of the tangent in between the point of intersection, the point of tangency, and an intersection point. So this here is a tangent segment. A secant segment is going to be the part of the secant that makes a chord. So basically just the part that's inside the circle. This is a secant segment. The external segment is very specifically the part of a secant that is outside of the circle. So this would be our external segment. Oops, sorry. I got these two mixed up. I apologize. The external segment would just go from here to here. It's the part of the secant that's outside of the circle. And I want to make one quick edit here. The secant segment is the entire part up until the point of intersection, not just the chord. Otherwise, we just call it a chord. So the secant segment is really this in red. So for definitions, we can say that the tangent segment is just a segment that is tangent to a circle at an endpoint. The secant segment is a segment connecting a chord to an external endpoint, and the external segment is just the part of a secant segment, the part of a secant segment outside the circle. There we go. Now that we've talked about tangent segments, secant segments, and external segments, we are now going to put them together with the segments of secant's theorem. Let's do a diagram first, and then we will talk about the actual definition. So let's say I draw a diagram here, and I want to draw two secant segments that intersect outside of the circle. So I'm thinking of drawing something that looks like this. An endpoint going all the way through, and another endpoint going all the way through. So these are two secant segments. It's like chords, but with an external segment. I'm going to label the following: B and A. I'm going to label the bottom one C and D, and I'm going to call the external point E. Just like the segments of chords theorem, the segments of secant's theorem says you can actually multiply bits of the secant together, and it'll equal the product of the other secant segments. So for instance, I can take AB and multiply it by AE. This would look like the following. I will actually write it as, I apologize. You can multiply the secant segment by the external segment. There, we should clarify. We can actually multiply together BE and AE, and it'll equal DE times CE. If I was to write this out, EB is the entire secant, whereas EA is the external part, and that's going to equal ED, this entire secant segment, times just the part that's external, EC. Definitionally, it goes like this. If two secant segments share the same external endpoint, meaning they meet at some spot outside of the circle, then the product of one secant segment and its external segment equals the product of the other. Multiply the entire secant segment by its external segment, and it'll equal the other secant segment times its external segment. let's take a look at exercise 2. So on exercise 2, we'll do let's just do part A together. In part A of exercise 2, no, I apologize, we'll do part A and part C. In exercise A, we see that we have two secant segments, RQ and RT. Well, the rule is that we can multiply an entire segment by its external part. So we can say, well, the entire segment is 9 plus 11, or 20. 20 times 9 would be our first segment. On the other side of things, we see that we have RT is the entire secant segment, whereas RS is just the external part of it. So we can say that that's going to equal RT is 10 plus X. Whereas RS is just 10. So it's not the easiest problem in the world. We still have to do some math here. But it is going to be fairly easy compared to some of the other problems we've done. Let's see it. 20 times 9 is just 180. 10 plus x times 10 just means we have to distribute the 10. We'll end up getting 100 plus 10x, because that 10 multiplies to everything. When we subtract 100 from both sides, we will end up getting 80 equals 10x. And to solve for x, divide by 10. X equals 8. Very nice. I'll let you do B on your own. I will let you know that for a problem such as B, you're going to get an answer fairly quickly. I do believe that for this one, we end up getting x equals 13 when everything is said and done. You can use that to check your answer. But I want to take a look at problem C. This is one that's going to be pretty difficult, actually. It's going to take us some time. So let's do it together. As a reminder, the entire segment times the external segment will equal the other segment times the external segment. So let's write out an expression for this top one. The entire segment is 3 plus x plus 2, which can be written as x plus 5. Meanwhile, the external segment part is just 3, so it's just x plus 5 times 3. But what about this bottom one? X plus 1 and x minus 1. When we add them together, x plus x is 2x. But 1 plus negative 1 is 0. So we know it's just going to be 2x for that one. On the other hand, we have to multiply it still by x plus 1. So we're actually going to get quite a bit of an expression here. 3 times x plus 5 is 3x plus 15. 2x times x plus 1 is 2x squared plus 2x. Uh-oh, we've got x's and x squareds. This is going to become a factoring problem very quickly. Start by moving everything to one side. So I'm going to subtract 3x and subtract 15 from both sides. It's going to give us 0 equals 2x squared minus x minus 15. And this is one that we will have to either factor or use the quadratic formula or complete the square in order to solve. I've always been a pretty big fan of factoring, and I think that it's going to be more helpful for you in Algebra 2 if you can practice factoring. So let's do this factoring together. We have an a value. It's bigger than 1. But we can't divide everything by that a value, so we have to use the AC method. Many of y'all have learned to use the AC method using a big X, so I will show you using that as well. On top, you put whatever you're multiplying to make, in other words, a times c. And on the bottom, you put whatever you're adding to make, our b value. Our a value is 2, our c value is negative 15, so we're trying to multiply two numbers to make negative 30. Our b value is just a negative sign, so it's negative 1. The only two numbers that can multiply together to make negative 30, but add to make negative 1, are negative 6 and positive 5. Remember, if your b value is really close to 0, it means your two mystery numbers are close together. So, when we factor this, the second step is always to split your middle term into your two mystery numbers. So when I rewrite this, we'll end up getting 0 equals 2x squared minus 6x plus 5x minus 15. The next step for the AC method is, as always, to group your terms, now that you have 4 of them, and take out what you can from each group. So here, I notice that both of these terms can be divided by 2 and x. So 2x is our GCF. Left over, I would have an x here and a minus 3 here. Here I notice 5x and negative 15 can both be divided by 5. So once again, I see what's left over. I'm left with an x and a negative 3. You know that you've done it right when these two match. So, to finish off the problem, our first factor is just 2x plus 5, because we took out of parentheses. Our second factor is x minus 3, because that was what was in parentheses. To simplify this, or to solve for x, I should say, set each factor equal to 0. We say that 2x plus 5 equals 0, and we see what we have when we actually solve that. I'll let you know right off the gate, we'll end up with x equaling negative 5 halves. And over here, x minus 3 would just give us 3. So these are the theoretical two answers for part C. But just like when you're using the quadratic formula, you can sometimes end up with extraneous solutions, solutions that don't make sense in the context of the problem. Negative 5 halves is like negative 2.5. Is it possible to have a segment that's negative 2.5 minus 1 units long? You can't have a negative 3.5 inch piece of wood, so why would we have it here? Negative 5 halves is extraneous because it simply does not actually fit into our diagram. But 3 works fine. That would mean this length is 2, this length is 4, and this length is 5. So 3 is the only reasonable answer. All right. Almost done, folks. We've got one more definition to go and then 2 more quick examples. Let's take a look at the segments of secants and tangents theorem. Now we are combining our secant segments with something else. But don't worry, it's actually a fairly reasonable theorem when you think about it. This theorem allows for us to have a tangent and a secant that we are dealing with. Let's say I have the following. Let's say that I call my tangent AE. And let's say I call my secant, I'll call the chord CD. Well, it's kind of like the segments of secant's theorem. For the segments of secant's theorem, we had the whole thing times the external part. But if we have tangent AE, the whole thing is the external part. A tangent is always external. So taking this theory from up above, we would have to do the entire tangent, EA, times whatever part is external, it's EA once again. And we would multiply our secant, the entire thing being ED and the external part being EC. But wait a second, EA times EA can be written more simply. The simplified rule is this. If you have a tangent and a secant that meet at an external point, your tangent squared, because again it's EA times EA, equals the entire secant segment, so ED, times the external part, the external segment of your secant segment, EC. Not nearly as bad as it looked. Now, the words are going to be a little bit tough because it's going to be a bit of a long definition, but it says if a secant segment and tangent segment share an endpoint, share an external endpoint, then the product of the secant segment and its external segment, that's to say ED times EC, equals the square of the tangent segment. So it really is the same definition, just used twice. It looks a little bit different, but we'll use it the same way. That's why if you were to write your note card for this test, we would only really technically need to write the segments of secants definition. So if I wanted to find the length of RS, we can solve this by just writing out an equation, the entire segment times the piece of a segment. Let's see what we can do. So, for this problem here, we end up with the entire segment for RT being x plus 8. That's the entire segment. Times the external part of the segment is just x. And it equals the tangent segment squared, because the entire tangent is 16 and the external part is 16. It's 16 times 16. So let's do this part together. 16 squared is 256, and x times x plus 8 is x squared plus 8x. Oh my goodness, we have yet another problem that's going to involve either factoring, completing the square, or the quadratic formula. X squared plus 8x minus 256 equals 0. Well, it's not the neatest one. And I'll be honest with you, I don't want to try and find factors of negative 256. I think that's a ridiculous thing to do. There, I said it. I put it out there in the world. So, if there's a problem that you don't want to factor, use the quadratic formula. The quadratic formula is, you're going to make me sing the song, so let's do it. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So, when we plug in each value here, our b value seems to be 8, so it'll be x is equal to negative 8 plus or minus the square root of 8 squared minus 4 times a. We don't have an a value. There's no number in front of our x squared. So 4 times 1 times c, which is negative 256, divided by 2a, or 2 times 1. Now, if you really wanted to, you could simplify this step by step by step by step by step. It's going to be a bit of a long one, just an FYI. But I do want to at least show you what we will end up getting. What we'll end up getting is we will have -8 plus or minus the square root of, whoops, sorry, I typed in my calculator wrong, plus this, 1088 divided by 2. What a crazy one. I'll also let you know, oh wait, that's not correct. Did I write that down incorrectly? 64 plus 4 times 256. No, that is correct, 1088. As we look through this problem, this is actually going to be the product of two very interesting terms. 1088 can actually be written as 64 times 16. How would we figure this out? You would have to just divide 1088 by different perfect squares until you find one that fits. I'll do the simplification over here in this little box, but 1088 can be rewritten as the square root of 64 times the square root of 17, because 64 times 17 is 1088. This gives us 8 root 17. So this whole thing just simplifies to -8 plus or minus 8 root 17 over 2. And since the -8 and 8 can both be divided by 2, our final answer is -4 plus or minus 4 root 17. Whew, what a crazy, crazy answer. And I'll let you know, this is going to be a case where only one of the answers actually makes sense. If I was to take a look at what -4 plus the square root, or -4 plus 4 root 17 is, we end up getting a positive number. If we end up doing it the other way, we end up getting a negative number. And since this length can't be negative, the only possible answer is -4 plus 4 root 17. When I type that into my calculator, I end up getting about 12.49. So x is about 12.49. There we go. Was this easier than factoring? That's really up to you. But I certainly would not be able to find factors that actually worked for this one, because we got such a strange number in the end. All right, let's take a look at the last problem. So, you probably would not remember this. In fact, you definitely don't remember this. You were certainly too young for it. Heck, even I'm too young for it. I was born in this year. The Cassini spacecraft, which launched in 1997, finally made its return back to Earth in October of 2017. This was a big, big deal. This was like the furthest out that humanity had ever gone from Earth. The spacecraft was used to study Saturn, including its rings and its moons. There are 3 moons on Saturn that we're going to be taking a look at: Tethys, Calypso, Telesto. They form a near perfect circle around Saturn, with a radius of the circle being about 295,000 kilometers. And we need to find the distance between Cassini and Tethys when Cassini and Telesto are tangent to the orbit, just like the diagram says. So really, we're looking for the distance BD in this diagram. It's a little hard to read on the black and white version, so I'm actually going to also go through the trouble of redrawing it. Here we go. And here we go. Oops, I accidentally drew my segment a bit too long, but that's okay. B, C, D, and A. Well, we know that the distance between C and D is 83,000 kilometers. We know the distance between A and D is 203,000 kilometers. And it tells us here that the radius of this circle, of its orbit, is 295,000. But there's no radius in this diagram, so we can't use it. Instead, we just have to call this x. We have a case of a tangent segment and a secant segment. So let's go through the rule. The rule is, take the entire secant, which is x plus 83,000, and multiply it by the external part of the secant segment. The 83,000 is the external segment. And that's going to equal your tangent segment squared, 203,000 kilometers. Believe it or not, this is actually going to be super easy to solve despite the bigger numbers, because there's only one x in this entire problem. When we multiply this out, we're going to get something very reasonable indeed. So 83,000 times x is 83,000x. 83,000 times 83,000 is going to give us a whopping 6,889,000,000. That is 6,889,000,000. No, I had it right the first time. 6,889,000,000 kilometers away. And that's going to equal 203,000 squared, which is going to give us quite a big number. In fact, you'll see that it gives us this in our calculators. A little reminder about scientific notation. That number after the E tells you how many places to move your decimal point to the right. So it's not 4.12. It's this number, 41209, after moving the decimal 10 places. So it's after the 1 that's 1 place, 2, 3. It'd be moved 4 places if it was right here. 5 after the 0, 6 after this 0, 7, 8, 9, 10. That's moved the decimal 10 places from where it originally was. So that's the number that we're working with. Luckily, we have all this in our calculator still. So I'm going to just do this answer minus this. I don't need to retype it because I just selected it, to give us a much more reasonable number. Maybe not much more, but a marginally more reasonable number. Again, it's E10, so I have to move the decimal point 10 places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And to find x, we just have to divide by 83,000. The correct answer for our problem is this. X, this part here, is equal to 413,493 kilometers, 0.9759. So is that the answer to our problem? Is that all done? Not exactly. You see, x is just the secant part of the secant segment. That's a chord. We need to find the entire secant segment. So we also need to add our 83,000 from the external segment. Not x, but the distance that we were trying to find, BD, is equal to 496,493 kilometers, basically 494 though. That's our answer. Whew, what a problem. That concludes our notes for today, folks. Thank you so much for listening, and have a great rest of your day.